that's the slide we did last time. We finished this one. But I want to explain what we are doing here. Just refresh your memory a little bit. What we are doing, we want to check linear independence given two functions, y1, y2. Yeah. Here we know y1, y2 are two of the solutions of above ODE. But our checking method could be applied on any two functions. Yeah. Yeah. Although here we want to develop some special checking method to check if two solutions are linearly independent. Yeah. But this method also it works for any two functions. We can apply this method, checking if they are linearly independent. Yeah. All right. So the idea, very simple. We take derivative because by the application of linearly independent, the definition, if you have K1, K2 linear combination of these two functions equal to 0 on some interval. That's important. Not on one point. Yeah. So, because this function could be 0 at one point. That's very easy. But on this whole interval, it equals 0. Then, that's very special. That's very special. Okay? Yeah. Because then, on the whole interval, this whole function equals to 0. Then we can take a derivative. Its derivative also equals 0 on the whole interval. Yeah. If at one point, you cannot say that. Okay? Yeah. If at one point equals 0, then you take derivative, you cannot say its derivative also equals 0. You cannot. But on whole interval, this function becomes a constant function. 0 constant function. So you take the derivative on a constant function, then it must be 0. Okay? Yeah. So this kind of little things. Yeah. Because when I give you quiz number 2, quiz number 2, you need to, some concept questions. I need to check your understanding on these little things. Yeah. Related to linear independence concept. Yeah. All right, yeah. Then we need to solve in order to determine K1, K2 constant. Because y1, y2, these two functions are known. Yeah. When we do the checking, they are known. Yeah. Yeah. We apply this checking method on two known functions. But K1, K2 are unknown. So we solve this linear system for K1, K2 unknowns. Yeah. To solve it, we like to write it in a matrix form. Yeah. So this matrix form linear system has a special property, homogeneous, because the right-hand side equals 0. So it's homogeneous. Yeah. So it's a homogeneous linear system. Yeah. Then in linear algebra, there is a very important result. Yeah. Although pretty simple, but it's very important. So we apply that important result here. For a homogeneous linear system to have a non-trivial solution. So here, we need to look at the non-trivial solution. Because this system always has the trivial solution. K1, 0, K2, 0. That's the trivial solution. Okay? K1, K2, both 0. We call the trivial solution. And this linear system always has the trivial solution. Yeah. Yeah. So we do not need to do anything. Yeah. But if it has a non-trivial solution, it depends. Sometimes it has a non-trivial solution. Sometimes it does not have non-trivial solution. Depends on some important condition we need to check. So what's that condition? Based on the linear algebra, that condition is the determinant of the coefficient matrix. Yeah. Here we treat this 2 by 2 matrix, the coefficient matrix of this linear system. So determinant of this 2 by 2 coefficient matrix is non-zero, then this homogeneous linear system does not have non-trivial solution. Not equal to 0, it implies it has no non-trivial solution. That's the result from linear algebra. Yeah. It's very simple to derive it. Yeah. Yeah. Later at some place, I will talk about this question again. Yeah. So I will explain why. Yeah. So this result, I will give you a little more explanation. Here, I just save some time. I'll give you this result. Later, we have another chance. I will explain more details on this result. All right. Yeah. So then we can check. Yeah. Because if this determinant is not equal to 0, then this linear system has only trivial solution. Then this linear combination, if it equals 0 on I, then K1, K2 must be both 0. Must be both 0. That means they are linearly independent. They are linearly independent. If K1, K2 not all 0 to make this whole function equal to 0 on I, they are linearly dependent. Linearly dependent on I. Okay? Outside I, we don't know. Okay? Yeah. So let me say again. Yeah. If there exists K1, K2 non-zero, yeah. If you can find non-zero K1, K2, yeah. Yeah. Here we can say both non-zero. Yeah. Why? Because if one equals 0, the other must be 0. Okay? Yeah, because left-hand side, right-hand side, right? Yeah, one term, K1 times y1 of x equals 0, because this y1 function cannot be a 0 function, right? So yeah, it's a, non-zero function. Yeah. Yeah. Our y1, y2, they are non-zero function. Okay? All right. Yeah. So then, if one equals 0, the other must be 0. Yeah. So for that reason, we say if find K1, K2 both non-zero to make this linear combination function be 0 on interval I, then these two functions, y1, y2, they must be linearly dependent. Yeah, try to, follow the logic. Yeah. So here, I just repeat the story last time, yeah, because a little tricky. Yeah. The logic here, so you need to, the deduction chain, there are many steps you need to understand. All the deduction steps here. All right, so let's move to the next slide. Linear dependence and independence of solutions. We can treat it as a summary. So this slide is the last slide of part B. After this slide, we will go to part C. So it's a summary slide. So we define Wronskian. determinant. Yeah, so that determinant. So we call it this W notation. W, Y1, Y2. So here we apply this Wronskian, the definition, on two functions. Yeah. But this definition can be easily generalized to three functions, n functions. Yeah, any number of functions. All right. Define in this way because this is the determinant formula. When you calculate determinant of that 2 by 2 matrix in the previous slide, this is the formula for the calculation. All right. Yeah. So here, I think just repeat that story. Yeah. So linearly dependent on. Oh yeah. All right. So here, not repeat that story. Here we look at the linearly dependent case on this I, interval I. If and only if the Wronskian is 0 at the sum x0 in I. Yeah, so this is the result. Yeah. Let us spend a few minutes to understand this whole result. Yeah. Because you may have a few questions in your quiz number 2 related to this result. All right, so let me complete it. Furthermore, complete it first. If W equals 0 at x equals 0 in I, yeah, all right, then W equals 0 on I. Okay? Hence, if there is an x1 in I at which W not equal to 0, then y1 are linearly independent. Yeah. So here, I need to really explain this result. Yeah. Because it's not easy to. It looks a little confusing. Yeah. Looks a little confusing. The main point that may cause confusion is 1 point and whole interval I. Yeah. So the main reason, sometimes you look at the 1 point, W equals 0 or not. Sometimes you look at the whole interval I, they are linearly dependent or independent. Yeah. That part may cause confusion. Yeah. Here, let me explain this confusion part. Yeah. All right. Yeah. Yeah. All right. So, yeah. So the first part. Yeah. All right. Yeah. Continuous. All right. Two continuous functions. All right. Opening interval. Two solutions. Y1, Y2. Yeah. Because based on that condition. First, remember, we learned existence uniqueness theorem, right? Yeah. Based on the condition, continuous functions, then we have the existence of these two solutions. Yeah. That's no problem. But now we want to see if they are linearly dependent on I. All right. Linearly dependent on I. The condition is if and only if. Yeah. So two-way. Yeah. So that means if the Wronskian equals 0 at some point. So here you can see when you check linearly dependent, here you only need to Wronskian equals 0 at 1 point. Some x0, that's 1 point. So in the whole interval I, you only need to find 1 point. And at this point, the Wronskian equals 0, then you have enough information to say these two functions are linearly dependent. Okay? Yeah. Dependent. All right? Yeah. Can you understand? Yeah. Yeah. Why so strong? Yeah. For linearly dependent property, yeah, we calculate the Wronskian. And we only need to see there is one. Right. Yeah, because Wronskian is supposed to be a function, right? Wronskian, after your calculation, it could be a function. This function, if it has 1 0 point inside the interval I, then it forces y1, y2 solutions linearly dependent. That's the meaning. Yeah. The first step, that's the meaning. Okay, I explain the meaning first. Second, I want to explain why it is true. Why we have a pretty strong result like this. Okay, think about when Wronskian equals 0 based on our linear algebra result in the previous slide. What's the conclusion? So that linear system has a non-trivial solution, right? K1, K2, non-trivial solution. We know K1 is a constant, K2 is a constant. K1, K2, by this 1 point, yeah, only at x0, this 1 point, the Wronskian equals 0, we already have enough information to tell us this K1, K2 are non-zero. Yeah, non-zero. Just a minute. K1, K2 is non-zero. Linearly dependent. Yeah. This part is a little, yeah. Okay, yeah. So this part is still, yeah, because at 1 point, non-zero. Yeah. Let me see. Yeah, that's part. Yeah. I think I need to. Yeah, I need to look at this part. Yeah, carefully. Yeah. All right. Yeah. Next time I try to explain this. Yeah, very confusing. Yeah. All right. Example, yeah. We know these are the two solutions, y1, y2. Yeah. Remember, we have the formula, okay? Characteristic equation. And the characteristic equation has has a double real root. Yeah. So called lambda minus 1 squared. This is its characteristic equation. So then, based on our formula, these two functions are two solutions. Now we want to check if the Wronskian is non-zero or not on the whole interval I. Yeah. So because this function can never be 0, right? E function can never be 0. Yeah, very simple checking. Yeah, and for that, yeah. So this part, I really need to find some easy way to explain. Yeah. So the point is 1 point and the whole interval. Yeah. Linearly dependent, linearly independent, and 1 point and the whole interval. Yeah. So these 4 things. Yeah. Very, very tricky. Yeah. Let me explain next time. All right. Yeah. That's the part B. Yeah. Now we go to part C. The title, the topic, Introduction to Laplace Transform. Yeah. So this is a very important topic. Yeah. C.1, basic properties of Laplace transform. Yeah. First, let me explain why we need to apply this Laplace transform. Yeah. All right. First, let's look at the motivation of this. Actually, this is a new technique. Yeah. New technique for solving ODE, yeah. Linear ODE. Yeah. Yeah. So linear ODE. Yeah. Yeah. And later, this technique can also be used to solve linear PDE. Yeah, PDE. So very important. All right. Then the idea. So the main idea, so powerful. So why it is so powerful? Yeah. Look at the second half of the sentence here. Yeah. Solving an ODE, if we apply this method, it can be simplified to an algebraic problem by the transformations method. Yeah. So there is a special method. Yeah. This idea, yeah, so important in math problem solving. Yeah. It's a completely new way to solve problems. Yeah. All right. So let me use a diagram to explain this idea. Yeah, Given initial value problem of ODE. All right. First, you do not solve it directly. So when you have such a problem, what do? The first step you do, you apply a Laplace transform. That's the first step. Okay? You apply Laplace transform. Yeah. Next slide, we will define Laplace transform. Yeah. At this point, yeah, you do not know what it looks like. Yeah. Then, this transform converts initial value problem ODE to an algebraic problem. Like magic. Yeah. After conversion, all the derivatives are gone. Derivatives disappear. All the derivatives. So what you have is a regular algebraic equation. And we feel much easier, right? Yeah. It is much easier to solve an algebraic equation than solving ODE, right? Yeah. ODE, too complicated. For solving algebraic equation, division, multiplication, that kind of manipulations, much easier. That's the power of this method. Yeah. All right. After that, we just solve algebraic problem. Okay? Yeah. Right. Yeah. Yeah. No derivatives, no integrals. Yeah. All right. Yeah. After that, then, but you need to go back to the solution of the original problem. you need an inverse Laplace transform. Okay? Yeah? You need to go back, right? So this step number 3, you need an inverse. Laplace transform. Okay? Yeah. Using some formulas. Yeah. Yeah. So we will learn Laplace transform of many basic functions and the inverse Laplace transform of many basic functions. Yeah. We just look up the table, okay? Yeah. Just like the, integral table things, yeah? Yeah. So we find appropriate formula, but we need to do some, form change. Yeah. Yeah. So that's the general idea. You can see in this diagram. Yeah. So it is very powerful. Yeah. It's a powerful method to solve ODE. Yeah. All right. This type of mathematics converts problem of calculus. Now, with derivatives, integrals, that's the problem of calculus, to algebraic problem. So no derivatives, no integrals, just algebraic operation. We can solve the equation. Yeah. All right. Yeah. Known as operational calculus. Yeah. All right. And then later, so this method, another powerful transformation method. Yeah. We also learned in this class, Fourier transform. Yeah. After midterm, we will learn Fourier transform. Before midterm, we learned this Laplace transform. Yeah. 2 very powerful methods, solving both ODE and PDE. These 2 methods. Yeah. All right. Main advantages. Yeah. 2 main advantages of this method. First, the problems are solved more directly comparing with our older methods, our old ways to solve ODEs. Yeah. More directly. How more directly? Initial value problems are solved without first determining a general solution. Our older method, we need to determine general solution. The general solution containing constant C1, C2, right? So we apply the initial conditions to find C1, C2 constant. That's our older method. Here, we do not need to do that. We can, when we set up equations, so this step, this transformation step, we need to apply the initial condition. Yeah. When we, take a Laplace transform, in our transformation formula, we need to use the initial condition. So when we get the algebraic problem, it already contains the initial condition there. Okay? Yeah. Then we just solve the algebraic equation directly. Yeah. So the difference of this method. Another important difference. Homogeneous ODEs, non-homogeneous ODEs are solved without first solving corresponding homogeneous ODE. Yeah? Our older method, you need to solve the homogeneous version first. Yeah. Then you need to, do another step to solve the non-homogeneous version. Yeah, but here, let's do all together. Okay? We do not separate homogeneous, non-homogeneous. We just, apply Laplace transform on everything in the equation. Yeah. So that's the one important difference. All right. Here, the method is particularly powerful for problems with inputs that have discontinuities. Yeah. Yeah. So this method can handle discontinuity of the functions well. Yeah. Yeah. So why is that? Yeah. because the definition of this Laplace transform, yeah, next slide we will do that. The definition of Laplace transform, we use integral to define Laplace transform. Yeah, integral can handle discontinuity well, right? Yeah, integral. Yeah. Yeah. So when you have, suppose your right-hand side, remember the right-hand side, R function, right? R function, right-hand side, contains some discontinuity points. Yeah. So then you take Laplace transform on that function with discontinuity points. Yeah. So we have some nice formulas to handle those discontinuities easily. Yeah. So that's another advantage. Yeah. Two important special functions that can represent discontinuity. Yeah, discontinuity function. The function could be very complicated, right? Discontinuity here and there, so anywhere, discontinuity. But we don't want to work on the complicated functions with discontinuities in special ways. So there is a simple way to handle all the discontinuities. One is the Heaviside function. Yeah, Heaviside function, although this name people may not be familiar, but it's a simple function like this. Okay? X, Y coordinate. Heaviside function, yeah, just like this. Yeah. The constant on the interval. This takes 1, okay? On the interval between AB, okay, AB. Then it takes 1 on the interval, then on all other points it's 0. Yeah? That simple function, yeah, called Heaviside function, but we can use this special function to represent, many, so the functions with all different discontinuities easily. Yeah. Then, when we take Laplace transform, yeah, we just need a formula apply on the Heaviside function. Okay? So we can, apply the formula. Yeah. So that's one. And there is another special function, the second special function. The first important is this Heaviside function. Second important, Dirac's delta function. Another special function, Dirac delta function. Yeah. This function, another important special function. Yeah. And this function, it's very hard to draw its graph. Yeah. Here I just, draw a little bit. Yeah. X, Y coordinate. Dirac delta function, okay? All right. And this origin, 0 point. So this function, very strange. Very strange. At all these points, this function 0, but only non-zero at the origin. Only 1 point non-zero origin, okay? Then it's like a peak. But at origin, so the peak, how large is the peak? Infinity. Goes to infinity. Yeah, so the Dirac delta function, we use this delta x represent. But there is a property, okay? The integral of this delta of x, integral equals 1. Such a strange function. Okay? The shape is like that. So it's hard to draw a good shape. Here I just give you some simple description here. There, integral. If you take integral on this delta function, you get a 1. Yeah. All right. Yeah. So here, actually, strictly speaking, yeah, so this we call a delta function. Strictly speaking, it is not a legitimate function. Yeah. Because if you apply the function definition, this delta function is not a valid function. No. How can a function take value at 0, infinity? No such function. Not a valid function. Okay? Yeah. Yeah. But this weird function is so useful in solving real-world problems, engineering problems. Many engineers, this function is so important, so useful. So people do not want to throw it away, right? Yeah, because it does not follow the normal function definition. No. You cannot apply normal definition of a function to check. Yeah. It does not follow the rules for a function. Okay? Yeah. For this reason, so most people give a different name. Do not call this a function directly. So it's called a generalized function. So it's not a regular function. It is not a regular function. It is a generalized function. Okay? So that's one name for it. Another name, yeah, some other mathematicians also call it a different name to separate it from the function. Call it a distribution. So it is a distribution. Yeah. So it's not a function. So give it another category. So it is a distribution. Yeah. So then they give a definition of distribution using integral to define distribution. Yeah. Integral is okay. So integral here. Yeah. So this is, distribution type definition. All right? Yeah. Yeah. This is a part of the definition. There is, other parts definition. Okay? Yeah. So it's a distribution, not a function. Okay? Yeah. But in solving engineering, PDE, ODE problems, very useful. Yeah. Yeah. All right. Yeah. Next. Now let's look at the definition of Laplace transform. Yeah. Integral. Yeah, we're using f of s. Yeah. The curly L, yeah, Laplace, the notation of little f is defined as integral from 0 to infinity. Then there is e function, e to the negative s times t. Yeah. That special part, yeah, special using that function to take a, there is a special role for this function. Okay? Then the targeted function, the function we are working on, little f function, yeah, dt. Yeah. Here you can see in this definition, yeah, we know variable t is the dummy variable, right? Yeah, dummy variable. Because after integration, it's gone. Okay? Variable t is used to do the integral calculation. Yeah. So we call it dummy variable. Yeah. And s is the real variable. Okay? Yeah. S. Yeah. And s, when we take the integral, we can treat s as a constant. Yeah. Because when we calculate the integral, we fix that s. We do not change the s. Yeah. Yeah. After you complete that integral, when we are here, we treat s as a variable. S can change. Yeah. So that understanding. So that's the transform way. Yeah. So what is a mathematical transform. So this way, typical mathematical transform. You have input, output, okay? Yeah. The input is your little f. Little f is your input. Yeah. So you push this little f as input into a black box, okay? Into the black box. Then inside the black box, you do something. Yeah. A lot of things. Then output is this capital F. Okay? Yeah. So two functions. So little f function, then capital F function. So, but how to connect them? Yeah. So you have this integral, okay, special operations to connect these two functions. Yeah. So that's one thing. Yeah. Yeah. Here we're try to understand this definition well. So mathematicians make this kernel concept. Because this E function part, it's a very special function. This function plays a very important role. Yeah. So mathematicians gave a concept name to it, kernel. So we call this function as a kernel. So what's that kernel? So here we use a special notation, define k of s and t, two variable function. It's a general kernel form. Okay? And in our Laplace transform, we make our general kernel function to be this e to the negative st function. Yeah. Later, when we want to consider other different mathematical transform, we change the kernel. Yeah. So we still use the pattern, this kind of pattern, all right? Fourier transform, later, we still use the integral, this pattern, but the main difference is we change to a different kernel. Then we get a different transform. Yeah. So this kind of understanding, yeah, very useful in math. Yeah. So then the general, yeah, if we use the kernel way to understand the mathematical transform, f of s equals, yeah. So here from 0 to infinity, but for Fourier transform, people can change this to negative infinity. Yeah? Modify it to negative infinity. Okay? Yeah. Yeah. But here, this situation, it's from 0. Okay? Yeah. The general case, yeah. So we can extend to negative infinity. Right. So this kernel apply, so then x. Yeah. Yeah. That's the transform. All right. Yeah. Then inverse Laplace transform. No. Eventually, we need to get back to the original solution, right? Yeah. So you need to apply inverse transform, Laplace transform. All right. So here, we need to know how to calculate inverse Laplace transform. All right. Notation. We use this L, yeah, inverse notation. Yeah. So that's the notation. But the question is how to calculate it. All right? How to calculate inverse Laplace. Yeah, that's important. Is there a definition in calculating inverse Laplace transform? Yeah, because people may like to know what is the specific definition. If we want to calculate inverse Laplace transform. No. It cannot be found. Not like Fourier transform. For the Fourier transform, if you want to find inverse Fourier transform, there is a specific formula. Okay? So you can calculate. But Laplace transform, no such formula. Nobody can find it. Yeah. But people can calculate inverse Laplace transform indirectly. Yeah, so here, when we calculate, we use the indirect way to calculate inverse Laplace transform. All right. For an inverse Laplace transform, it must satisfy the basic property. Here, these two equalities, they are basic properties of inverse operation. Yeah. For any inverse operation, you have to you have these two equalities. Yeah. So you apply the original operation. After it, you apply inverse operation directly. You go back, you get the same thing. So your output is the same as the input because that's the meaning of inverse, right? Yeah. Inverse. So you recover to your original object. That's the meaning of inverse. Okay? Yeah. Yeah. Then another version. Yeah. Suppose you have an object at the transformed side. Yeah. Here there are two. Yeah. So here, in order to understand the second equality, this time you need to have another level understanding. Yeah. Here, this part I understand a little abstract. Yeah. But I still like you go through this kind of abstract understanding. Because later we apply formulas. Yeah. Later when we apply Laplace transform to solve ODEs, all we need to do, formulas, always formulas. Okay? Yeah. Yeah. But here I want to give you some basic understanding before we go to all formula calculations. Yeah. So here, I draw a line to separate two different, yeah. So here, yeah, I need to use a special name here, yeah. Domains. Okay, yeah. So two different domains here, okay, to separate. Yeah. Before transformation, yeah. So your function stays in a certain domain, right? Yeah. Yeah. So the f function, we use a t variable. Okay. T variable, stays in certain domain. Okay. Sometimes people call time domain. T, it's a time variable. So t represents time. Okay. Yeah. Or, sometimes it represents x coordinate. Okay. Yeah. So that's what we call a domain, right? Yeah. Time domain. Sometimes people call time domain. Okay. Yeah. If it's x, spatial domain. Okay. Time domain or spatial domain. Yeah. But after you apply transformation, yeah. So here Laplace transformation, you go to a different domain. Okay? Yeah. So capital F of S. Yeah. Why people change a different variable from t to s? Because it represents this time the domain of your function has been changed. Completely different domain. Okay? Yeah. So this understanding, important, background, useful in your background. So here, this domain, typically people use one commonly used domain is the time domain. Okay? Another is spatial domain. Okay? All right. This side, S cannot be time domain, cannot be spatial domain. All right? Yeah. Yeah. So most of the time people call it frequency domain. Frequency domain. Okay? Yeah, yeah. In image processing, Fourier transform, image processing, you get a frequency domain. So different domains, all right? Yeah. With that concept, yeah. Now let's understand this last equality. Now we can understand a little better. Yeah. First, we get a capital F function. It's in the frequency domain, okay? Yeah. So our capital function, yeah, is applied on frequency domain. That object. So we apply inverse Laplace transform. Inverse Laplace transform to bring it back to this domain, okay? Yeah. So this direction, inverse Laplace transform. There. Bring it back to time domain or spatial domain. All right? Yeah. Okay. All right. And so one function. Yeah. So here, yeah. So we can imagine some appropriate little f function in time domain or spatial domain. Okay. After inverse Laplace transform. Then you apply Laplace transform on this little f function on time domain, spatial domain, then you go back to the original capital F function in frequency domain. Yeah, so that's the second equality. So the first equality, second equality. Okay, yeah. So you use this diagram to understand. Yeah. All right. Yeah. Background, yeah. So this part for class relatively deep, yeah, because the mathematical thoughts in this part are very deep, yeah, very important, very deep, yeah, yeah. So very powerful. Yeah. So we need to, appreciate this kind of powerful mathematical thinking. Yeah, very valuable. Yeah. So that's why I spent quite some time explaining this part before we are ready to work on the formulas for Laplace transform. Yeah. Starting from our second half, then all we will do many formulas. Yeah. We'll work on all different formulas. Then when we work on formulas, then you do not need this kind of background. Yeah. Yeah. You do not need to use this background. Yeah. Just work on the symbols. Yeah. Formula plugging here, there, and manipulation, algebraic operations. That's all you need to do when you solve problems. Yeah. Yeah, but this background, I feel, so you need to know that. Yeah. You need to know this part. Yeah. Although I do not give you test questions or homework questions for this background part. Yeah. Yeah. All right, so let's take a break, and you come back at 7:50.